welcome to Talk Tensors.
It's great to be here for this one.
So usually when we look at a broken bone on an X-ray, the diagnosis is clean, right? Like it's binary.
Yeah, exactly. The jagged white line is either there or, it is.
Right. But today, on your graduate level deep dive into machine learning research, we are stepping away from those clean grid-like images.
We are definitely heading into much murkier waters today.
Yeah, you really are, because when you step into the world of complex systems, so social networks, biological pathways, neurodevelopment, that X-ray machine is just utterly useless.
Oh, completely. You can't just look at one isolated bone anymore.
Exactly. You have to look at how every single bone, muscle, and nerve communicates with literally everything else. And as always, our mission here is to cut through the noise, skip the superficial abstracts, and get straight into the methodology.
The real math, the results, and, well, the lasting legacy of some truly seminal computer science research.
Spot on. And just a quick reminder for you listening, a link to the original research we're discussing today is available right down in the description.
So that diagnostic muddy water you just mentioned, that's actually the perfect framing for the exact problem computer scientists were facing back in the late 2010s.
Right, because they were desperately trying to model the real world, but the mathematical tools they had built were, well, they were designed for artificial perfection.
Yeah, so we are transporting you back to late 2017. If you remember that era of machine learning, convolutional neural networks, or CNNs, were just viewed as this unstoppable force.
Oh, totally. Image classification, semantic segmentation, machine translation. CNNs were absolutely dominating everything.
And they were dominating specifically because of the underlying structure of the data they were being fed, right?
Right, because if you have an image, you have a grid of pixels. It is mathematically uniform.
Exactly. A CNN exploits that uniformity beautifully. It uses these local filters that just slide across the grid, mathematically summarizing local pixel neighborhoods.
Because every pixel right in the middle of a 2D image is surrounded by exactly 8 other pixels, right? It's always uniform.
Yeah, so the network can learn a single set of parameters, like a single filter, and just reuse it across the entire image. It's highly efficient, highly parallelizable.
And translationally invariant.
Yes. But the massive catch, the wall they hit, is that the natural world rarely organizes itself into a perfect grid.
I mean, think about the data structures that actually govern our lives, like a telecommunications network routing data globally.
Or a social network, right, where one user follows maybe 10 close friends, but then a celebrity follows 10 million accounts.
Exactly. Or think about 3D meshes for computer graphics, or the biological connectome of the human brain. These domains just don't fit into neat little pixel squares.
No, they're graphs. They consist of nodes connected by edges in completely arbitrary, messy, totally unpredictable topologies.
And researchers were just hitting a massive wall trying to figure out how to map the immense power of deep neural networks onto these irregular graphs. The whole field was fractured.
It really was. The state of the art was fundamentally split into 2 camps that were effectively at war with each other. And each side was championing a method that had a fatal flaw.
And meanwhile, completely separate from these graph theory wars, the natural language processing world had just experienced a seismic shift.
Oh, yeah. A team led by Ashish Vaswani at Google had just published Attention is All You Need,
which introduced the transformer architecture, proving that self-attention mechanisms could model complex relationships without needing, recurrent sequences.
Right, which sets the stage perfectly for the breakthrough we are analyzing today. We are covering the introduction of graph attention networks, or GATs.
Yeah, this paper, which was spearheaded by researchers from the University of Cambridge and the Montreal Institute for Learning Algorithms.
A team that actually included Yoshua Bengio, notably.
Right. They managed to thread the needle. They successfully married graph-structured data with masked self-attention.
The core thesis here, right, is that this architecture allows nodes to dynamically weigh the importance of their neighbors.
And crucially, it does this without relying on costly matrix operations or needing to know the global graph structure up front.
It provided this elegant, computationally brilliant solution that honestly solved the most rigid constraints of that era's graph modeling attempts.
But to truly appreciate why the graph attention network was such a revelation, we kind of need to examine the specific flavor of misery that graph researchers were dealing with before it arrived.
Yeah, we have to look at those 2 warring camps, the spectral approaches and the spatial approaches.
So let's start with the spectral camp. This includes the pioneering work by Joan Bruna in 2014, the refinements by Michael Deferard using Chebyshev polynomials.
And ultimately, this really famous graph convolutional network, or GCN, introduced by Kipf and Welling.
Right. The spectral approach is conceptually fascinating, but it's mathematically really heavy.
Very heavy. It attempts to define convolutions not in the spatial domain, meaning not by looking at physical neighbors, but in the Fourier domain.
So the core engine of this math relies on computing the eigendecomposition of the graph Laplacian.
Right. Let's break down that concept for a second, because it is the fundamental trap of the spectral method. The graph Laplacian isn't just some random matrix.
No, you can think of it as a mathematical description of how energy or heat diffuses across a specific network.
Exactly. If you drop a unit of heat on node A, the graph Laplacian dictates exactly how fast that heat will spread to node B, node C, and so on, based on the specific edges connecting them.
Right, and because the Laplacian describes the diffusion of energy across the entirety of the graph, its eigendecomposition, the fundamental frequencies, is inextricably linked to the global architecture of that exact network.
Yeah, and Kipf and Welling achieved a massive breakthrough with the GCN by approximating these spectral filters using a first-order approximation.
Which meant the math was drastically simplified. The filters only had to operate on a node's immediate one-step neighborhood rather than calculating global diffusion every single time.
But, and this is the big but, the ghost of the Laplacian was still in the machine. Even with the approximation, the learned filters of a GCN are fundamentally dependent on the Laplacian eigenbasis of the graph it was trained on.
Which creates what is known as a strictly transductive learning environment.
Right. If you train a GCN on a specific citation network, it learns the structural geometry of that exact network.
But if you then hand the model a completely new unseen graph, like a network of proteins instead of papers, the model entirely breaks down.
It totally fails. The underlying frequency domain has changed, so the filters are now completely useless. It cannot generalize to unseen topologies.
It's honestly the equivalent of memorizing the exact layout of the London Underground. You spend weeks training and you know flawlessly how the Central Line connects to the Victoria Line. You're highly efficient.
But the second you step off a plane in Tokyo, a city with a completely unseen subway structure, you are entirely lost.
Exactly. Your navigation skills were rigidly transductive. They completely depended on the fixed structure of London.
And that transductive constraint is exactly what drove researchers toward the second camp, the spatial or non-spectral approaches.
Right. These researchers argued that instead of dealing with global Laplacians and Fourier domains, the network should just look at a node's immediate neighbors in physical spatial proximity.
Yeah, much like a standard CNN does with pixels. And the heavyweight champion of the spatial camp at the time was GraphSAGE.
Introduced by Will Hamilton and Jer Leskebek, and GraphSAGE was designed specifically to be inductive.
Yes, it was meant to learn the actual rules of navigation, how to read street signs, how traffic flows so it could be dropped into Tokyo and still function perfectly fine.
But it ran into the variable neighborhood problem, because how do you build a uniform mathematical operator when one node has 2 neighbors and another has 2,000?
GraphSAGE tried to solve this through fixed-size neighborhood sampling. During training, if a node had 1,000 neighbors, the algorithm would randomly sample a fixed number.
Say exactly 25 of them.
Right. It forced the unpredictable geometry of the graph into a uniform shape so the tensor math could actually execute smoothly.
So, returning to our navigation analogy, if you arrive at a massive, complex intersection in a new city, GraphSAGE doesn't look at the whole intersection. It randomly selects exactly 5 locals standing nearby and asks them for directions.
Which is incredibly risky. If you're fortunate, one of those 5 people is a taxi driver who knows the entire grid.
But if you are unlucky, you just sampled 5 lost tourists while the local expert was standing right next to them, completely ignored by your algorithm.
Exactly. You lose the full context of the neighborhood. The network is essentially blind to the actual density and nuance of the graph.
And furthermore, to aggregate the information from those sampled neighbors, the highest performing variant of GraphSAGE used an LSTM, a long short-term memory network.
Which introduces an entirely new logical fallacy. I mean, LSTMs are engineered specifically for sequence modeling.
Right. They're designed to process the order of words in a sentence, or the chronological ticks of time series data.
So by feeding spatial neighbors into an LSTM aggregator, the architecture implicitly assumes that there is a sequential ordered relationship among a node's connections.
It assumes that friend A is sequentially prior to friend B in a social network, which is nonsense.
Total nonsense. The authors of GraphSAGE were aware of this, obviously, and they attempted to mitigate it by feeding randomly ordered permutations of the neighbors into the LSTM during training,
hoping to force the network to become invariant to the order, but it was a computationally expensive and frankly clunky workaround for a fundamental architectural mismatch.
It's the definition of forcing a square peg into a round hole. You had these brilliant researchers bending backward to accommodate the flaws in their frameworks.
Which perfectly defines the tension of the era. The machine learning community desperately needed an operator that could simultaneously achieve three things.
Right. First, it had to handle variable-sized neighborhoods without arbitrarily dropping vital information like GraphSAGE did.
Second, it needed to maintain shared, learnable weights to keep the parameter count efficient, mimicking the best properties of a CNN.
And third, it had to operate inductively. It needed to generalize to completely unseen graphs without requiring the global graph Laplacian up front, like the GCN.
And the graph attentional layer was the architectural key that unlocked all three of those doors simultaneously.
It really was. Let's dissect the mechanics of this layer. We're going to walk through the exact mathematical pipeline.
Yeah, let's translate the linear algebra into the actual conceptual operations that allow these nodes to communicate.
The beauty of the paper really lies in the modularity of its core mechanism. The researchers designed a single building block, the graph attentional layer,
which can be stacked sequentially to build an arbitrarily deep graph attention network.
Exactly. So we begin with the input state. Imagine a vast interconnected graph. We're going to zoom in and focus entirely on the perspective of one specific entity within this graph. Let's call it node I.
Okay, node I. And node I possesses a set of intrinsic characteristics, right? Its features.
Yes. In the mathematical notation of the paper, this is represented as a feature vector, H sub I.
So if we're analyzing a massive social media network, this vector might contain scalar values representing the user's account age, their daily posting frequency, and maybe their total follower count.
Exactly. Let's define the total number of these initial features as F. So the layer receives an input matrix containing the feature vectors for all n nodes present in the graph.
But before any communication happens across the edges before node I even acknowledges its neighbors, the network forces every single node to undergo a linear transformation.
Right. This is achieved by multiplying every node's input feature vector, H sub I, by a shared learnable weight matrix, W.
And the objective here is feature projection, right? The raw initial features might not be in a format that makes relational comparisons easy.
Exactly. The weight matrix projects the original F features into a higher level, more expressive latent space, resulting in a new vector with F prime features.
And because this exact same weight matrix W is applied universally to every single node in the graph, the model maintains translation invariance.
And it keeps the total parameter count highly efficient.
So every node in the network has basically put on a new mathematically transformed uniform. What happens next?
Now comes the critical mechanism. Self-attention. The network needs to compute a raw attention coefficient, denoted as E sub ij.
Okay, and this value represents the directional importance of node J's features to node I.
Yes. It essentially answers the question, how much should node I alter its own understanding of the world based on what node J looks like?
So how does it calculate that raw score?
To calculate this raw coefficient, the layer takes the newly transformed feature vector of node I and the transformed feature vector of node J and concatenates them.
It physically glues the two vectors together end to end.
Exactly. This combined representation is then fed into a shared attentional mechanism, represented by the variable A.
And in this specific architecture, the attentional mechanism is actually pretty simple, right? It's just a single layer feed-forward neural network.
Yeah, parameterized by a weight vector. It processes the concatenated features and outputs a single scalar value, the raw score E sub I.
But the architectural genius isn't just in the calculation of the score. It's in where the model chooses to calculate it.
Right. In the original Transformer paper designed for natural language, attention is global. Every single word in a paragraph computes an attention score with every other word in that paragraph.
So if the word is bank, it checks its relationship with the word river, 20 words away, and the word money, 50 words away. Every word attends to every word.
Yes, but the graph attention network explicitly rejects this global approach. It utilizes masked attention.
Wait, why mask the attention? In language models, global attention is the whole point.
Well, the computational reality of graph theory basically demands it. In a dense language model, processing a few thousand words, calculating global attention, which scales quadratically, is expensive, but it's feasible. But if you attempt to compute global attention on a biological graph containing hundreds of thousands of proteins, allowing every protein to evaluate every other protein, regardless of whether a physical connection even exists, the computational complexity just explodes.
Ah, right. The memory footprint becomes completely impossible to manage.
Exactly. By masking the attention, the architects placed a hard constraint on the network. Node I is only permitted to compute an attention score E sub ij if node j exists within its immediate first-order neighborhood.
It only evaluates nodes that are explicitly connected to it by an edge, along with evaluating itself, of course.
Yes. This masking completely severs the reliance on the global graph structure. The network doesn't need to know the shape of the entire universe. It only looks at the local roads that actually exist.
Which is brilliant because consequently, the time complexity of the layer drops to a highly manageable level. The computational cost scales linearly with the number of nodes plus the number of edges.
It achieves the exact same computational efficiency as the highly constrained GCN, but entirely without the transductive shackles. It only spends computing power evaluating the connections that are physically there.
Okay, so once the network has calculated these raw attention scores for a node's entire local neighborhood, what's next? Because raw outputs from a feed-forward layer are entirely unconstrained, right?
Yes, they face a massive scaling problem. In one neighborhood, the raw scores might range from 50 to 100. In a different neighborhood, they might range from -10 to 2.
To make these scores actually comparable and stable across the entire graph, they have to be normalized.
Exactly. The layer passes the raw scores of node E's neighborhood through a softmax function. This mathematical operation squashes all the raw values into a probability distribution.
So the outputs are scaled so that they all add up to exactly 1.0. These final normalized attention coefficients are denoted as alpha sub I.
But before the softmax is applied, there's a very crucial hyperparameter injected into the pipeline, a leaky rel-LU nonlinearity.
Right. The authors specify a leaky rel-U with a negative input slope of exactly 0.2. This is a vital empirical detail for network stability, isn't it?
It is. If they had used a standard rel-U activation function, any negative raw attention score would be aggressively clamped to absolute zero.
Which introduces the dying rel-U problem. If a node consistently outputs negative scores, it gets clamped to zero, which means during the backpropagation phase, no gradient can flow backward through that pathway to update the weights.
The node effectively dies. It stops learning permanently.
So why does a slope of exactly 0.2 solve this?
It acts as a mathematical pressure valve. Instead of clamping negative values to zero, the leaky rel-U allows a small proportional trickle of information to pass through.
So if the raw score is -10, the function outputs -2.
Exactly. This ensures that even for extremely weak or seemingly irrelevant connections, a tiny gradient still flows backward during training, allowing the weight matrices to continue updating and adjusting.
And the 0.2 value is just an empirically derived sweet spot.
Yes, large enough to keep the gradients alive, but small enough to ensure that highly relevant positive connections still dominate the softmax distribution.
Okay, so we now have our normalized weights, our alpha sub ij values. The final phase of the layer is the output. How does node I actually use these weights to update its own identity?
It performs a linear combination. Node I takes the transformed feature vectors of all its neighbors, multiplies each one by its specific normalized attention weight alpha sub I, and then just sums the results together.
To visualize this, let's say Node is a junior researcher in a citation network. It looks at the papers it has cited.
Okay.
The attention mechanism determines that neighbor J is a highly relevant foundational piece of literature, assigning it an alpha sub ij weight of 0.85. Meanwhile, it assigns a weight of only 0.05 to 3 other mathematically tangential papers.
Right, so Node I essentially absorbs 85% of its new identity from the foundational paper, heavily adopting its features, while mostly ignoring the noise of the tangential citations.
And after applying one final nonlinearity, like an ELU activation function, Node I has successfully generated its new hidden representation. The graph attentional layer has executed completely.
It has. It accommodated variable-sized neighborhoods seamlessly because the softmax function simply normalizes whatever number of neighbors happen to be present.
It maintained shared weights, and it operated entirely inductively, based solely on local edge presence. It is a phenomenal piece of engineering.
It really is. However, Anyone who has trained a deep neural network knows that relying on a single attention computation can be a highly brittle strategy.
Oh, yeah. The optimization landscape of deep learning is incredibly noisy. If that single feed-forward attention mechanism happens to get stuck in a poor local minimum early in training,
Or if it just fixates on a totally misleading feature, the entire representation of that node is permanently corrupted.
and the authors anticipated this instability. To ensure the network learned robust, multifaceted representations, they integrated a concept directly from the transformer architecture: multi-head attention.
Yes. Instead of initializing a single attention mechanism to evaluate the neighborhood, they initialize K entirely independent attention mechanisms.
I like to conceptualize multi-head attention as assembling a corporate board of directors. Imagine Node I as a CEO, and it needs to evaluate a potential merger with a target company, Node J.
Okay, I like this analogy.
If the CEO only asks their chief financial officer for an opinion, they receive a highly specific, narrow evaluation based purely on revenue streams and debt structures. That is single-head attention.
And while the financial evaluation might be accurate, it might completely blind the CEO to the fact that the target company holds a revolutionary new engineering patent or, suffers from deeply problematic management liabilities.
Precisely why you build a board. You deploy K independent experts. You ask the financial expert, the legal expert, the engineering lead, and the marketing director to all look at the exact same target company, the exact same raw node features.
And they all apply their own unique weight matrices. The financial head might compute a massive attention score for Node J, while the engineering head ignores Node J entirely and directs all its attention weight toward a different neighbor, Node K.
Right. The K attention mechanisms execute their transformations simultaneously and independently across the neighborhood.
The architectural challenge then becomes how to aggregate those independent evaluations. The GATT paper handles the outputs of these multiple heads differently depending on the layer's position within the overall network architecture.
So let's look at the intermediate hidden layers first. How do they combine the board's for ports while the information is still flowing deeper into the network?
In the hidden layers, the outputs are concatenated. They're literally attached end to end.
So if the architecture utilizes 8 independent attention heads, and each head projects the input into a feature vector of length 8, the network concatenates them to produce a single, dense, 64-dimensional feature vector for node I.
Exactly. By concatenating them, the network preserves the distinct, nuanced perspectives of all the experts.
The financial data isn't mixed with the legal data. They are kept separate but bundled together, allowing the next layer of the network to decide which expert's perspective is most valuable for further abstraction.
But that concatenation strategy completely falls apart at the final prediction layer.
Right, because if the ultimate goal of the network is to classify a node into one of 7 distinct categories, you can't output a massive concatenated 64-dimensional vector.
No, the network needs to collapse the multifaceted analysis into a single, unified consensus.
So in the final classification layer, the board of directors is forced to take a vote.
Yes. Instead of concatenating, the network computes the element-wise average of the feature vectors produced by the K-heads.
It averages their scores and then applies the final classification nonlinearity, like a softmax function, to output the final probability distribution over the target classes.
And this averaging process smooths out anomalies, prevents the model from overfitting to the idiosyncrasies of any single attention head, and massively stabilizes the training trajectory.
Okay, so with the theoretical architecture fully defined and stabilized, the authors had to prove its efficacy. I mean, theoretical elegance in machine learning is basically meaningless if the model cannot survive contact with real adversarial data distributions.
Absolutely. So they subjected the graph attention network to rigorous benchmarking against the absolute pinnacle models of 2017.
They evaluated the model across 2 fundamentally different experimental paradigms: transductive learning and inductive learning. We need to dissect these datasets to understand the scale of what they achieved.
Let's examine the transductive proving grounds first. The authors utilized 3 classic citation network datasets: Cora, CiteSeer, and PubMed.
In these environments, the objective is node classification specifically, predicting the overarching topic or subfield of a scientific document.
Right. In these graphs, a node represents a single research paper, and an undirected edge represents a citation linking 2 papers together.
Let's look at the specific dimensions. The core data set consists of 2,708 nodes, and each node is represented by 1,433 features. But I want to pause on those features because they aren't the dense embeddings like we use today. The paper utilizes a bag of words representation.
Yeah, the bag of words technique is a foundational, somewhat primitive natural language processing method. The researchers define a static dictionary of 1,433 unique, highly relevant technical terms.
Okay.
For every document in the graph, they generate a vector of length 1,433. If word number 42, let's say the word gradient, appears anywhere in the text of the document, the vector receives a 1 at position 42. If the word is absent, it receives a 0.
It entirely strips away the grammatical structure, the context, and the sequential order of the text. It simply asks a binary question. Are these specific vocabulary words present in the document's bag?
Exactly. That sparse vector serves as the H sub I input for the network. Cora challenges the model to classify these sparse vectors into 7 different topic classes.
And CiteSeer is slightly more complex, containing 3,327 nodes, over 3,700 features per node, and 6 target classes. PubMed represents the largest transductive challenge, scaling up to 19,717 nodes categorized into 3 classes, though it only provides 500 features per node.
But the most critical aspect of this transductive setup is how aggressively the authors starved the model of training data.
Yeah, this is wild. For the training phase, the algorithm is only provided with the true labels of 20 nodes per class.
That is an incredibly severe constraint. In the Cora dataset, across all 7 topic classes, the model only has 140 labeled examples to learn from.
However, because this is a transductive experimental design, the training algorithm is permitted to observe the feature vectors, the sparse bag of words of all 2,708 nodes in the graph, as well as the complete structural map of all citations. It simply is denied access to their true topic labels.
Right. To return to our city analogy, the model is given the complete architectural blueprint of the entire city. It knows every street and every intersection.
However, it only knows the actual names of 20 specific restaurants within each district. It has to infer the identities of all the remaining thousands of buildings based purely on their structural proximity and their sparse features.
It is a really robust test of semi-supervised learning. But the authors knew that matching GCNs on transductive citation networks was merely table stakes.
The true gauntlet, the arena where they intended to prove the absolute superiority of their architecture over spatial methods like GraphSAGE, was the inductive dataset.
Yes, they selected a dataset from computational biology, PPI, or protein-protein interaction,
which shifts the paradigm entirely. It consists of 24 distinct graphs, each representing the protein interaction networks within different human tissues. The nodes are individual proteins, and an edge signifies that 2 proteins physically and chemically interact within that specific biological tissue.
And the scale and complexity here just dwarfs the citation networks. Of the 24 graphs, 20 are utilized for training, 2 are held out for validation, and 2 are reserved strictly for testing. The 20 training graphs contained a combined total of nearly 45,000 nodes.
And here is the defining mechanism of the inductive benchmark. The 2 testing graphs, representing completely different human tissues, remained entirely unobserved during the training process.
The network never sees their edge topology. It never processes their node features. They are kept locked in a vault until the final inference phase.
And the feature representations of these proteins are also vastly more complex than a simple bag of words. Each protein node contains exactly 50 dense features. These features represent deep biological markers.
Right. They include positional gene sets, which indicate the physical location of the gene on the chromosome that encodes the protein.
They include immunological signatures, which map how the protein responds to various cellular stress factors. And critically, they include motif gene sets.
Let's explain motif gene sets because it highlights the difficulty of the task. A motif isn't just a random sequence. It is a highly conserved recurring pattern of amino acids that holds a specific evolutionary biological function.
So if a protein has a specific structural motif, it might be designed to bind directly to DNA. So the network is being fed these dense functional blueprints.
And the classification task itself is a total nightmare compared to Cora. It is a multi-label classification problem spanning 121 possible labels derived from gene ontology.
Meaning a protein does not have a single mutually exclusive identity. A protein might act as a structural component of the cell membrane while simultaneously functioning as a receptor for a signaling pathway, while simultaneously playing a role in cellular metabolism.
And the network must predict all 121 binary states for every single node simultaneously.
I really want to emphasize the stakes of this specific benchmark. This is not a theoretical computer science exercise in data sorting.
No, not at all.
If a model succeeds on the transductive Cora dataset, it proves it can effectively organize a library of PDFs. That is a useful administrative tool. But if a model succeeds on the inductive PPI dataset, it proves that it can learn the fundamental physics, the biochemical rules of how proteins interact within one set of human tissues, and then successfully predict the behavior of entirely new proteins in a totally alien biological environment that it has never encountered before.
It is the absolute dividing line between algorithmic memorization and transferable scientific reasoning.
So with the architecture built and the gauntlets defined, we reach the moment of truth. Let's look at the hard results of the experiments.
On the transductive citation networks, the authors deployed GAT against a massive, comprehensive lineup of baseline models to ensure a rigorous comparison.
They tested against label propagation, semi-supervised embeddings, and the iterative classification algorithm. And they also tested against DeepWalk.
DeepWalk is a really fascinating comparison point. DeepWalk attempted to process graphs by treating them exactly like natural language.
Right, it would deploy a random walker onto a node. The walker would randomly traverse the edges of the graph, recording the ID of every node it visited.
This created a sequence of nodes, essentially a sentence describing the graph's local geometry. DeepWalk would then feed these structural sentences into a word-to-vec algorithm to learn continuous embeddings for the nodes.
It was a highly clever approach to forcing graph data into NLP architectures, but GAT consistently outperformed it. GAT also defeated manifold regularization, planetoid, and the higher-order Chebyshev polynomial filters.
However, the benchmark the entire community was watching was a direct head-to-head matchup. GAT versus the reigning spectral champion, the GCN.
The results were definitive but nuanced. On the Cora dataset, GAT achieved a classification accuracy of 83.0%. The optimal GCN configuration achieved 81.5%.
On the CiteSeer network, GAT reached 72.5%, surpassing GCNs at 70.3%.
And on the PubMed dataset, the two architectures effectively tied, with GAT scoring 79.0% against GCN's identical 79.0%.
Okay, so
Actually, I have to play the skeptic here. We are looking at a 1.5% accuracy increase on Cora and a 2.2% increase on CiteSeer. From a statistical perspective, it is a measurable victory. But does a 1.5% bump genuinely justify the introduction of an entirely new mathematical paradigm? Is that an evolutionary step or a revolutionary leap?
that's a totally fair, necessary question.
Oh.
If we isolate the transductive results, they represent an evolutionary refinement. They empirically prove that the capacity to assign heterogeneous weights to different neighbors, the core feature of GAT that GCN structurally cannot execute, provides a tangible increase in model expressivity. But you are correct to be skeptical. The transductive fixed graph environment was always the native domain of the GCN. Beating the GCN on its home turf by a few percentage points was merely establishing baseline credibility. The revolutionary leap, the data point that permanently altered the trajectory of the field, occurred in the inductive setting.
The protein-protein interaction dataset.
Exactly. On the entirely unseen zero-shot PPI test graphs, the performance metric used is the microaverage F1 score.
And the F1 score is a critical metric for multi-label problems where the classes might be severely imbalanced. It is the harmonic mean of precision and recall.
Right. It effectively measures a model's ability to accurately identify positive instances without drowning in false positives. The scale goes from 0.0 to 1.0, representing absolute predictive perfection.
Prior to this paper, the highest performing inductive model in the world was GraphSAGE utilizing the LSTM aggregator. That model achieved an F1 score of 0.612 on the PPI dataset.
The researchers behind GAT actually re-engineered the GraphSAGE architecture, optimizing its hyperparameters and pushing it to its theoretical limits, managing to elevate its score to 0.768.
Let's cement that number. 0.768 represented the absolute ceiling of spatial inductive graph learning at the time.
And the graph attention network achieved an F1 score of 0.973.
0.973. That is not a 1.5% incremental bump. That is a colossal, landscape-shattering 20.5% margin of victory over the most heavily optimized GraphSAGE setup.
It was an algorithmic demolition. It proved, beyond any shadow of mathematical doubt, that observing the entirety of a node's neighborhood and dynamically weighting those connections via self-attention is vastly, overwhelmingly superior to GraphSAGE's methodology of randomly sampling a fixed number of neighbors.
The fixed sampling approach was actively discarding vital, determinative biological information.
Yes. The attention mechanism preserved all local structural information, but learned precisely what subsets of that information to prioritize and what to mathematically silence.
The scale of that victory is staggering. And what makes this paper a classic is that the authors didn't just publish the high score and walk away. They engineered an ablation study to mathematically isolate and prove exactly why the performance leaped so drastically.
Right. They designed a crippled variant of their own architecture, which they named const-get.
The constant attention mechanism. They retained the exact architecture of the GAT, the linear transformations, the multi-head setup, but they fundamentally neutered the attentional feed-forward network.
They basically lobotomized the model. They forced the mechanism to assign the exact same uniform weight to every single neighbor in the receptive field. Mathematically, the attention coefficient always equated to a constant value.
By forcing uniform weights, they essentially devolved the GAT back into a massive inductive GCN.
And the performance drop isolated the value of the attention mechanism perfectly. The const-GAT achieved an F1 score of 0.934. The fully functional GAT, equipped with dynamic attention, achieved 0.973.
That 3.9% differential represents the pure, isolated computational value of the attention mechanism itself.
It definitively proves that the specific ability to calculate, neighbor A's motif is highly determinative of my function, whereas neighbor B's positional gene set is entirely irrelevant to my current state, is the primary driver of the model's superior performance.
Beyond the raw F1 scores, the authors provided a qualitative visual proof that I find deeply compelling. They wanted to understand what the network was actually seeing inside its hidden layers.
Yeah, this part is brilliant. They extracted the high-dimensional feature representations generated by the very first layer of a GAT model trained on the Cora dataset.
And they projected those high-dimensional vectors down into a 2D visual space using a dimensionality reduction algorithm called TSNE.
Right. TSNE, or T-distributed stochastic neighbor embedding, is an incredibly powerful tool for understanding latent spaces. If two nodes have evolved mathematically similar representations within the 64-dimensional hidden layer of the GAT, the TSNE algorithm attempts to place them physically close together on a 2D scatter plot.
We've examined the resulting image in the source material, and it essentially looks like a pointillism painting. Imagine a white canvas scattered with thousands of small colored dots.
Every single dot represents a distinct research paper in the core network. The colors of the dots correspond to the 7 true underlying topic classes of the dataset: green for neural networks, pink for rule learning, orange for reinforcement learning, and so on.
Now, it is crucial to remember that the GAT network was never explicitly instructed to group these nodes by color within its hidden layer. It was merely executing its attention calculations to optimize its final loss function.
Yet, the TSNE projection reveals 7 highly distinct, geographically separated clusters.
The visual separation is striking. You see a massive, highly dense green cluster dominating the upper middle quadrant of the space. There is a tight, highly concentrated pink cluster isolated on the far left. An elongated, swooping orange cluster stretches across the middle.
The network has organically learned to cluster mathematically similar papers together based purely on their structural connections and sparse features.
But the authors added a brilliant layer of detail to the visualization. Within these colored clusters, you can see the physical edges, the citations connecting the papers drawn as faint blue lines.
However, the authors dynamically modulated the thickness of those edge lines based directly on the strength of the aggregated attention coefficients, the alpha sub A's values calculated by the multi-head mechanism.
By doing so, they essentially rendered the network's internal thought process visible. You can physically see the flow of attention.
The thickest, darkest lines are heavily concentrated deep within the centers of the monochromatic clusters, where papers of the exact same topic are citing one another.
The network has learned to assign massive mathematical weight to neighbors that share its underlying latent scientific class.
Conversely, when a citation edge crosses the void between two totally different topic clusters, say, a neural network paper citing a completely unrelated rule learning paper, the line is drawn incredibly thin.
The network computes the attention score and mathematically ignores the cross-disciplinary noise.
It is elegant, undeniable visual proof of the model's discriminative power. It demonstrates that the masked self-attention mechanism is successfully learning the true underlying semantic geometry of the data, rather than just blindly aggregating nearby signals.
It is a masterpiece of architectural design. However, as we consistently explore on talk tensors, No paper, regardless of its brilliance, is without flaws. Every significant breakthrough is inherently constrained by the technological realities of the era it was born into.
Absolutely.
We need to examine the limitations, the acknowledged blind spots, and the ultimate legacy of this work.
The authors were highly transparent about the bottlenecks they encountered. Interestingly, their primary adversary was not a theoretical flaw in their mathematics. Their primary adversary was the engineering constraints of 2017 software.
Specifically, the tensor manipulation frameworks of the time, such as the early iterations of TensorFlow, suffered from a severe optimization bottleneck regarding sparse matrix multiplication.
Let's translate the reality of that bottleneck. To process graph data efficiently without running out of memory, you must use sparse matrices.
A sparse matrix only stores the coordinates of the actual connections, rather than allocating memory for a massive grid of mostly zeros representing edges that don't exist.
In a standard setup, this requires a rank 2 tensor, which is effectively a standard 2D flat matrix of rows and columns.
But the inductive PPI dataset isn't just one graph, it's 24 separate graphs. To train a deep neural network efficiently on that dataset, you need to process multiple graphs simultaneously in a single forward pass. You need to utilize batching.
And to batch multiple graphs into a single tensor operation, you have to add a third dimension. You move from a flat rank 2 tensor to a rank 3 tensor, batch size by nodes by nodes.
I think of it like reading maps. A rank 2 tensor operation is like a computer pulling out a single flat map of a city, calculating all the routes, putting it away, and then pulling out the next flat map. It's slow.
A rank 3 tensor operation allows the computer to stack 24 maps on top of each other, creating a 3D hologram, and instantly calculate the routes through all 24 cities simultaneously.
But the software libraries of 2017 could not perform sparse matrix multiplication on those rank 3 tensors efficiently. The underlying CUDA kernels hadn't been optimized for it.
This systemic software failure severely crippled their batching capabilities. They were forced to use a minuscule batch size of merely 2 graphs during the intensive inductive training process, drastically increasing their training times and preventing them from leveraging the full parallel power of their GPUs.
They designed a mathematically brilliant engine, but they were forced to drive it on software infrastructure that simply hadn't caught up to their theory.
They also documented a theoretical inefficiency inherent to their design: redundant computation. In highly dense, heavily connected graphs, such as certain types of social networks where communities form tight cliques, the local neighborhoods of individual nodes heavily overlap.
If node A and node B are best friends, they likely share 90% of the exact same friend group.
Precisely. And because the GATT architecture parallelizes the attention computations across all edges independently, the multi-head attention mechanisms end up recomputing the exact same feature transformations and similarity scores for those shared friends multiple times across different nodes.
The architecture, in its original form, lacked a mechanism to cache and share those overlapping computations, leading to wasted cycles in dense topologies.
Furthermore, GATs suffer from the exact same fundamental constraint regarding their receptive field that plagues GCNs. A node's ability to see out into the wider graph is strictly capped by the depth of the network.
A 2-layer GAT can only gather information from its immediate neighbors and the neighbors of those neighbors. It is entirely blind to a critical piece of information located 3 hops away.
If you attempt to solve that by simply stacking more layers, building a 10-layer GAT, you run headfirst into the phenomenon of over-smoothing. With too many layers of aggregation, the node representations become excessively diluted, and eventually, every node in the graph starts to possess the exact same mathematical embedding, destroying the model's ability to classify anything.
The authors mitigated this somewhat by incorporating skip connections similar to the architecture of ResNets, which allowed them to successfully train a 3-layer model for the PPI dataset. But the receptive field remains a rigid architectural boundary.
We also have to acknowledge the absolute blind spots of the original paper. The model was engineered exclusively for the task of node classification. It evaluates a graph and assigns a label to the distinct entities within it.
It was not structurally designed for graph classification tasks, such as analyzing the holistic structure of an entire molecule and predicting whether the compound as a whole is toxic or safe.
And perhaps most significantly, the original GAT formulation completely ignored the concept of edge features.
In countless real-world scenarios, the connection itself contains vital, highly dimensional data. In a financial transaction network, an edge isn't merely a binary line indicating that account A transferred money to account B.
That edge possesses intrinsic features, a specific dollar amount, a precise microsecond timestamp, currency type, and an IP address.
The mathematical pipeline of the 2017 JAT viewed edges merely as structural pathways that permitted attention to flow between nodes. It possessed no mechanism to incorporate the edge's own rich features into the attention calculation.
Yet despite these engineering constraints and theoretical blind spots, the momentum generated by this paper was entirely unstoppable. This specific architectural design laid the absolute bedrock foundation for the entire modern paradigm of graph transformers.
The intellectual legacy of the single paper is inescapable. The fundamental insight that edges in any arbitrary, chaotic structure can be leveraged as pathways for masked self-attention has become entirely ubiquitous.
If you open a major social media platform today, or interact with a modern e-commerce recommendation engine that suggests products based on complex user interactions, you are directly interacting with the descendants of the graph attention network.
In the realm of computational biology, the legacy is even more profound. Systems designed to predict novel drug interactions or models engineered to map the exact protein misfolding pathways responsible for neurodegenerative diseases rely heavily on this exact inductive attention-based framework.
The authors successfully proved that the brilliance of NLP attention mechanisms could be seamlessly and powerfully mapped onto the chaotic, irregular geometry of the natural world.
That lasting legacy provides the perfect segue into the final phase of our deep dive. With the historical and mathematical foundation firmly established, it is time to push the boundaries of what these algorithms could theoretically achieve tomorrow. It is time for our signature segment, Novel Notions.
As always, we must explicitly state a disclaimer for this segment. The following ideas are entirely speculative intellectual explorations designed purely for entertainment purposes. We are not proposing peer-reviewed methodology. Rather, we are extrapolating the extreme logical conclusions of the GAT's underlying mechanics.
My first theoretical pitch is dynamic echo chamber disruption via adversarial GATs. Let's unpack the mechanics of this. We established during our analysis of the TSNE plot that GATs are phenomenally adept at identifying and reinforcing latent clusters.
The attention weights naturally group similar nodes together.
What if we applied a GAT to a live social media network, but we inverted the algorithm's objective function?
That is a highly provocative concept. Walk me through the technical mechanism. How do you invert it?
The operational core of the GAT is the alpha sub ij normalization equation, the softmax function that mathematically forces a node's attention across its neighborhood to sum to 1.0. Imagine a severe political echo chamber on a social network.
Okay.
A user node, I might technically follow 500 different accounts. However, algorithmically, their alpha sub ij values have become hyper-concentrated. The network's diagnostic layer realizes that node is applying 99% of its mathematical attention weight to just 3 highly polarizing, radicalizing neighbors, while assigning an effective weight of 0 to the remaining 497 diverse accounts.
From a purely mathematical standpoint, that represents a severe cognitive bottleneck within the graph. The user's latent representation, their updated state, is being entirely dominated by a microscopic fraction of their available network.
Exactly the problem. So instead of utilizing the GAT merely to predict what radical content node I will click on next, we deploy the GAT as a real-time structural diagnostic tool.
When the network flags that an individual's alpha sub ij concentration has exceeded a specific mathematical toxicity threshold, the system triggers an automated architectural intervention.
The immediate challenge there is execution. How do you intervene without resorting to blunt censorship? If the platform simply deletes the edges connecting node I to its 3 polarizing neighbors, you shatter the user's trust, violate their agency, and ultimately fracture the network's user base.
You do not delete a single edge, you do not censor a single post. Instead, you introduce adversarial synthetic nodes into the graph during the live inference phase.
Explain the engineering behind a synthetic node in this context.
The system engineers a temporary, entirely synthetic neighbor node and physically drops it into node's first-order receptive field. The synthetic node isn't a bot, it's a mathematical construct designed using gradient descent.
Its specific purpose is to maximize its own raw E sub I attention score with node I. It accomplishes this by projecting feature vectors representing synthesized content that perfectly align with node I's linear transformation matrix W.
However, the actual semantic content originates from just slightly outside the user's established echo chamber cluster.
The brilliance of that approach lies entirely in the physics of the softmax function. Because the normalized attention weights alpha sub I must definitively sum to exactly 1.00, attention is a zero-sum game.
If the highly optimized adversarial node successfully captures 20% of node's attention weight through sheer mathematical alignment, the softmax equation forces the attention weights allocated to the three polarizing neighbors to decrease proportionally.
It dilutes the echo chamber at the fundamental architectural level. The multi-head intention mechanisms are mathematically compelled to redistribute their weights away from the extremes.
The user experiences zero censorship. They are simply and naturally exposed to an optimized gradient of diverse information that subtly fractures the filter bubble. We are using the physics of the attention mechanism to architecturally enforce cognitive diversity.
A social algorithm that repairs polarization organically through weight redistribution rather than through heavy-handed content moderation. You are utilizing the mechanism of the disease hyper-concentrated attention as the foundation for the cure. I find the implications of that profound.
Let's move to idea number 2. We are shifting from sociology back to computational biology. I call this temporal GATs for real-time protein folding trajectories.
This connects directly to the inductive legacy of the 2017 paper. The authors established beyond a doubt that GATs absolutely dominate static PPI graphs, achieving that 0.973 F1 score. But biological reality is not static. Let's explore expanding this architecture into 4 dimensions.
What is the core concept here?
Rather than analyzing a human tissue sample as a static graph that is frozen at a single moment in time, we reconceptualize an unfolding amino acid chain as a highly dynamic, wildly unstable temporal graph.
The physical process of a protein folding into its functional 3D shape occurs in a fraction of a millisecond. During that microsecond window, the physical edges between amino acids are forming, breaking, and violently reforming as the chain twists and collapses into itself.
So the fundamental topology of the graph is shifting frame by frame. The original GATT paper relied entirely on a fixed neighborhood structure during a single forward pass. How does the architecture accommodate a topology that is constantly mutating?
We merged the inductive power of the GATT with a temporal masking mechanism, heavily inspired by the causal masking utilized in modern autoregressive large language models.
In an LLM, the attention mask prevents a word from attending to words that haven't been generated yet. In our theoretical temporal GATT, the mask slides continuously across a 4D tensor. We feed the network high-resolution, high-speed molecular dynamics simulations of the folding process.
The input is no longer just end nodes. It is end nodes existing across t discrete time steps.
The analytical focus then shifts completely. We are no longer observing just the final folded structure to see which proteins interact. The experiment focuses on tracking how the K different attention heads shift and modulate their alpha subarrays dynamically, frame by frame, throughout the folding trajectory. We are analyzing the derivatives of the attention weights.
The rate of change of attention becomes the primary signal. If we deploy this architecture to analyze a protein known to cause a severe misfolding disease, such as Alzheimer's or Huntington's, we might uncover a fleeting anomaly.
We might discover that at exactly microsecond 42 of the folding process, attention head number 3 experiences an abnormal, massive spike in its alpha sub-I weight, locking onto a false chemical edge and subsequently dragging the entire molecular structure down a pathological folding pathway.
It would act as a high-speed camera for molecular intention. It would reveal the intermediate ghost structures, the highly unstable, fleeting graph topologies that actually cause the disease, structures that are entirely invisible to static final state analysis.
If you isolate the exact microsecond and the exact node responsible for that pathological attention spike, you could theoretically engineer a pharmacological compound that acts as a mathematical blocker. A drug designed to physically bind to that specific amino acid sequence just milliseconds before the attention spike occurs, preventing the false edge from forming.
It represents a shift from predicting static biological states to mapping the real-time calculus of molecular formation. It honors the inductive leap made by the original Cambridge and Mila teams and extends their mathematical framework into the dimension of time.
Which brings us to the close of our journey today. We began this deep dive by discussing the comforting binary precision of a medical X-ray and how the massive arbitrary connections of complex real-world networks shatter that simplicity.
Graph attention networks provided the field with an entirely new kind of diagnostic machine, one that doesn't just statically map the bones of a system, but dynamically calculates how much every single component of that system is actively listening to its neighbors.
The paper definitively proved that structural topology does not equal destiny. By granting nodes the mathematical agency to actively weight the importance of their surroundings, The GAT proved that we can discover highly ordered discriminative patterns hidden deep within irregular chaos.
And it leaves us with a final, lingering thought. The legacy of GATs proved that the state of a node isn't defined merely by who its neighbors are, but by precisely how much attention it allocates to them.
As we continue to build increasingly massive neural graphs to model collective human behavior, global economic movements, and eventually the biological connectome of the human brain itself, we have to ask a fundamental question. Are we simply mimicking biological structures to build better predictive algorithms? Or are we, equation by equation, finally decoding the underlying mathematics of human focus?
Incredibly provocative thought to mull over.
Thank you for joining us on Talk Tensors. Keep questioning the structure, and we will see you on the next deep dive.